All right, so this is the lab three, part three, um, flat plate at a 10-degree angle. So I'm going to go ahead and open up the geometry, and I already have the geometry from the first or lab two, I should say. All right, here. First, I'm going to do is press the body, and then go to sketching. So since you want to create a flat plate right around the middle, 10 degrees, go ahead and draw a reference line. And then I'll start about right here, give it an angle. And then go to the dimensions. There's that one. And that one. Now, in the lab description, it gave a test section height of around 6 inches. And since you want to get a 10% blockage ratio, we can convert that. So 10% of 6 inches is around 1.52 centimeters. And then for the length, we just do a nice 8 centimeters. That's it's a nice, decent flat plate. And then we want to obviously do uh, the we want to do the oops, no, we want to do the angle of attack. So it's going to be right angle plus 10 degrees. So creates an angle of attack of 90 degrees, or sorry, 10 degrees. And then I'm gonna go ahead and maybe move this. Here's more right in the center of this test section. I'm gonna go ahead and remove the center line now. Use the trim tool. And that's about good. So generate, and then I'll unsuppress the body and see the changes have taken effect. We have the new plate there. And we can go ahead and close out of this. And now we'll open up the mesh. All right. All right, here we are. And so we want to do a triangular method. So go to mesh here, go to method, and then click the geometry, and then apply that. Instead of quadrilateral dominant, we'll go triangles. All right, so good. Back to mesh. And for the sake of this video, we want to do a pretty high number for the element size. So I already have it set to 0.01, so we could just keep that as is. Just again, for the sake of the video, I'll speed things up. And then we can generate that. All right, there we are. Now we can name our sections. So go here and then just hold control, and then click all of these. And then go down here, create name selection. And we can call this internal. All right. And then now we can create the housing, or sorry, name the housing. Call that just whoop, that walls. Very nice. Here we can call this velocity inlet. And then last but not least, the outlet. Let's call that outlet. We can go down here and we can check. Yep, everything, all the naming convention is applied. Looks like we're good to go. Go ahead and update. Mesh translation to Fluent is successful. All right, so we'll go ahead and just close out of this. And now we can go to setup. So launch the Fluent launcher and then make sure to have double precision. All right. You can see the new mesh is loaded. We have the plate there. And same settings as lab 2. So we'll go down to models, energy on, viscous, and since we want to do this at or since we want the inlet velocity to be at around 60 hertz for the fan, go down here, go to inlet, velocity inlet, click on that, and the I already have it here, already set up, but the inlet velocity at 30 hertz or 60 hertz, sorry, is around 3.37. Apply that, close. And since everything is set up from lab 2, everything is pretty much good to go. One thing we will want to do though is create a port definition for the drag. So you can just click new. I already have one right here, but you can just click new, and then it'll bring up this page. Then you want drag force, drag coefficient, either way on the internal. That's for just the plate. And since we haven't simulated it yet, so we can't compute that just yet. And that's pretty much it. Go to initialization. Initialize it. Obviously, it's pretty large element size, so it's gonna take very little amount of time to initialize and actually simulate. So that's good. And then run calculations. And I'll do around modest 300 iterations. It's pretty, like I said, pretty large element size, so it shouldn't even take that long. Might even converge before then. All right, sweet. Okay, and since you want the velocity contour and the streamline patterns and the static pressure, go down to graph or graphics, go to contours, and we just take everything here, the static pressure. I don't know why intake is there, and then compute, and then display. You can see the results there. And then for the vectors, since we want an arrow style, we went with filled arrow on everything again. Compute, and then display that. And we can see the results right there. And we also want the streamline pattern. So we can go to path lines. I have one set up here. And we just want the velocity or the streamlines from the velocity inlet. So we can do that one. And there we go. You can see the streamlines from the velocity hitting the plate, going over and creating a pretty large wake. And we also want the drag. So from earlier when we set this up, go to here now, and then could just click compute, make sure it's on internal, and we get the coefficient of drag, and do drag force. And obviously it's a bit high because we used a rather large element size, and also it's a little higher frequency of velocity. Or rather not velocity, but rather fan power, which creates higher velocity. And that's about it. Yeah, thank you. And here we go.